The following video is the first day of simplifying radicals for Honors Algebra 2 Trig. We're going to talk about radicals. The first thing we're going to do is talk about the relationship to exponents because we all kind of know what exponents are. So what is happening is a radical. So for example, the square root of 36 is really the same thing as 36 to the 1/2 power. And the cube root of 8 is really the same thing as 8 to the 1/3 power. Now, we're not going to talk about this too much anymore until the next chapter or a couple chapters next semester, but we want to be aware that radicals are really just a, a reorienting of exponents so that now we can have fractional exponents as something that are things. And so the square root of 36 is 6 because if I have 6 squared, and I have that to the 1/2 power, I can multiply the exponents just like I always did when I have a power to a power back in Algebra 1 or in 8th grade or 7th grade or wherever you learned about exponents and their rules. So not only can we identify radicals as something where we have, if we're doing the square root, that means that I need two of them to kind of come out. So for example, 36, 6 times 6 will end up making me take one of them out. Now, if I have a cubed root, I need three copies of that, or three factors multiplied by each other that are all the same in order to take it out. So the cube root of 8 is 2, because 2 times 2 times 2 is 8, and that can end up taking it out, which likewise with exponents, 2 cubed to the 1/3 power, if I multiply the exponents, 3 times 1/3 gives me an exponent of 1. And so if I look at square root is the same thing as 1/2 power, cube root is the same thing as 1/3 power, fourth root is the same thing as the 1/4 power, and so on. So to answer the next two questions, is the square root of a negative number a real number? We already know that that answer is no. And what about any even root? Well, this is something that if I have the square root of -8, I already know that would be square root of 8 times I, or 2 times square root of 2 times I. We already know that from the quadratics chapter, but that works for any power. So if I had the fourth root or the sixth root or the eighth root or whatever, I still wouldn't be able to do anything with that because if, for example, I have the fourth root of, let's say, -16, I can't somehow take this number on the inside and multiply the same number by itself 4 times and end up getting -16. No matter what, if I have 4 negative numbers multiplied by each other, it's always going to end up being positive. So I can't get an even number of the same number multiplied by itself to somehow be negative unless I have an imaginary number in there. But if I take a look at uh, an odd power, I can get an odd number of numbers that are multiplied by each other to be negative. So, for example, -2 times -2 times -2 does equal -8. So this works for odd radical powers, but it doesn't work for even radical powers. So odd powered roots, I can deal with negative numbers on the inside. Even powered roots, I would need imaginary numbers. And in this chapter, we're not really talking about imaginary numbers. So let's evaluate. The cube root of 512, well, I have to figure out what the cube root of 512 is. So 512 is really 8 cubed. So the cube root of 512 is going to be 8 because 8 times 8 times 8 gives me 512. If you are not aware that 8 times 8 times 8 is 512, that's okay. But by the time the test rolls around, you need to know your perfect squares and your perfect cubes, probably up through at least 10. So your perfect squares, you're probably going to want to know up through about 15, and your perfect cubes, you're going to want to know up through about 10. Okay, number 2, the cubed root of -27, we should know is -3. And then if I take that to the fourth power, -3 times -3 times -3 times -3 equals 81. One of the tricks of doing these problems is you always want to do the root first, because that makes the number small, and then you can make it bigger. If you try and do -27 to the fourth power first, that's going to be a nightmare. That makes it really, really large and really hard to deal with. So you always want to do the root first to make the number smaller at the beginning. The square root of 16 is 4. 4 cubed is 64. Now in this problem, the cubed root of 64 over the cubed root of 5 cubed. I could end up simplifying this at the beginning, but that would actually make the problem harder, because I know that the cubed root of 64 is 4, because 4 times 4 times 4 is 64. And the cubed root of 5 cubed is going to be 5. That's something to keep in mind. Anytime you have something in exponential form on the inside, and it's the same power on the outside, you don't really have to do a whole lot of work. The cube root of 5 cubed is going to be 5. So the answer there is 4/5. Simplify and leave in radical form. So if we want to simplify the square root of 80, I need to find the biggest perfect square that goes into 80. If I were going to do something to the fifth power over a number 6, I want the biggest number that is multiplied by itself 5 times that goes into 672. So we'll deal with that in a second. The biggest perfect square that goes into 80 is 16. So I have 4 multiplied by itself twice and then a 5 left over. I can write this as 4 times the square root of 5. That's going to be my final answer. Number 6, if I have 672, I need to try the numbers that are going to multiply together 5 times and possibly get into 672. So let's try 2 to the 5th first. 2 to the 5th is 32. If I take a look at 672, I need to kind of figure out if that is divisible by 32. So I'm just going to do a little side calculation. That's a 2, so 64. That gives me 32. So it looks like it does break down into 2 to the 5th times something else. So it ends up being 2 to the 5th times 21. So after I do some long division and figure that out, so this ends up being 2 to the 5th times 21. So 2 times 2 times 2 times 2 times 2, and then I have a 21. Well, if I have 2 to the 5th, that can get pulled out of the radical as a regular 2. And then this 21 is left over. 21 is really 3 times 7. I can't really do anything with 3 times 7 because I don't have 5 copies of 3 or 5 copies of 7. So that's my final answer. Number 7 and 8, we're just going to break down things with variables also. So if I take a look at number 7, 72, the biggest perfect square, since this is a square root, that goes into 72 is 36. So that's 6 times 6. So I'm going to have a 6 on the outside of the radical and a 2 left over on the inside of the radical. X to the 5th is really x times x times x times x times x. I have 2 pairs of x's, both of which can move to the outside. So I have an x squared that can move to the outside, and there's an x that's left over on the inside. Y squared is really y times y, so I get 1 copy of y that can move to the outside. I have no other copies of y that are left on the inside. So my final answer is 6x squared y times the square root of 2x. Number 8 is similar, except I need 3 copies of something in order to pull it out. 125 is 5 cubed. So that is a 5 getting pulled to the outside and nothing left over on the inside, because there are no numbers that are left over without a group of 3 that can take it out. W to the 4th is W times W times W times W. So 3 copies of W grouped together means that 1 W gets moved to the outside and there's 1 W left on the inside. X to the 9th is 3x cubed. So that means 3 copies of x cubed all grouped together, and I can move 3 x's to the outside. So it's x to the third power. Y to the fifth is y cubed times y squared. This y cubed means I can move 1 y to the outside, and I have 2 y's left over on the inside. And z squared, I don't have 3 copies of z, so that means I keep all of those on the inside. So if I rewrite my final answer, it's 5w x cubed y times the cube root of w y squared z squared. And that is my final answer. Number 9 and number 10, I'm now going to maneuver with simplifying things that are multiplied together. 18 is really 9 times 2, which is 3 times 3. So notice I don't have any groups of 3 that I can pull out of 18. 15 is 3 times 5. Since I'm going to multiply all these things together, what I notice is that I have 3 groups or 3 copies of 3 that if I multiplied these two things together, so 18 times 15, I could have as, what would that be? That would be 15 times 15 is 225, 270. So cube root of 270, hopefully that's right. But if I multiplied it together, I would end up doing the exact same thing coming down, where I would have 27 times 10, and that breaks into 3 times 3 times 3, and this breaks into 5 times 2. So notice I have the exact same numbers. It just saves me a step if I don't multiply it all out together at the beginning. So I have 3 copies of 3. They get to move to the outside, and then everything that's left over, a 2 and a 5, gets multiplied together, and on the inside I have 10. Notice that would be the same thing if I multiplied it together first. Number 7, I need 4 copies of something in order to move it out. So 14 is 7 times 2. 32 is 2 or 5 copies of 2. So I actually have one group of 4 copies of 2, and then I have 2 copies of 2 that are left over. So this 2 can move to the outside, which will get multiplied by the 7 and 4 that are already on the outside. So 7 times 4 is 28, times this 2 ends up being 56 on the outside. Left on the inside, I have 7 times 4. So I have a 28 left on the inside of the fourth root. Then I have x cubed and x to the 11th. That's x to the 14th. I need groups of 4. So I can break this up into x to the 12th times x squared. This is 3 copies of a group of 4. So that's x to the 4th, x to the 4th, x to the 4th. So that means I can pull an x cubed out, and I'm left with 2 copies of x squared on the inside. So my final answer is 56x cubed times the fourth root of 28, x squared. Adding radicals, if I have the exact same radical part, I can just add the parts together. This is kind of like saying 2x plus 6x. So if the radicals are the same, I can kind of treat it like it's a variable. So this would end up being 8 times the cube root of 4. Likewise, in number 12, I have negative 7 fourth root of 50 plus 1 fourth root of 50. That's negative 6 times the fourth root of 50. But if I have situations where I have unlike radicals, I have to try and break those down as much as I possibly can. So 108 is 27 times 4. 27 is 3 times 3 times 3. So I can rewrite this as 3 times the cube root of 4. 32 is 8 times 4, or 2 to the 5th. But these 3 copies of 2 can move to the outside. So I can have a 2 on the outside times the cube root of 4. Since I now have common radicals, I can add this together and add the coefficients together, basically. And I have 5 times the cube root of 4 is my final answer. Number 14, 8 square root of 5 minus, if I look at 45, that's 9 times 5, so that's the same thing as 3 times the square root of 5. And then root 20 is the same thing as 4 and 5, 2 and 2. So I pull out a 2, which gets multiplied by the 2 that's already there. So this ends up being plus 4 root 5. So if I rewrite this, I have 8 root 5 minus 3 root 5 plus 4 root 5. So I have 8 minus 3 plus 4, which ends up being 9. And then my radical part, since it was all the same, I'm allowed to just kind of keep that, treat it like a variable. So it's 9 times the square root of 5. Number 15, the square root of 1/4 is 1/2. I don't need to do a whole lot of uh, difficult calculations there because the square root of 1 over the square root of 4 is just 1/2. However, if I have something like 16, square root of 1 over square root of 5 is equal to 1 over the square root of 5. I'm not allowed to have any radicals in the denominator, so what I'm going to do is I'm going to multiply by a FFU, and that FFU that I'm going to multiply by is root 5 over root 5, because I know that the square root of 5 times the square root of 5 gives me regular 5. So the denominator is now 5, and the numerator is 1 times root 5, which is square root of 5. So my final answer for number 16 is root 5 over 5. In number 17, I have the cube root of 2 divided by the cube root of 9. So I need to get rid of the radical from the denominator. Notice that the cube root of 9 is really the cubed root of 3 squared. So how many more 3's do I need in order to make the denominator a nice number? I need to get 3 3's on the inside of the radical. I have 2. I need 1 more. So I'm going to multiply the top and bottom by the cube root of 3. Because if I look at the denominator now, it ends up being the cube root of 27, which ends up being a nice number. So the denominator is now 3. The numerator, when I multiply cube root of 2 times cube root of 3, when I multiply those things together, I end up getting the cube root of 6, because when I multiply, I can just multiply the numbers on the inside of the radical. 18, the cube root of 1 over the cube root of 5 is 1 over the cube root of 5, because the cube root of 1 is just 1. Now, I only have 1 5 in the denominator. I need 2 more 5's in the denominator in order to get a group of 3 cube root of 5's in order to make it a nice number. So if I have the cube root of 5, I need to multiply it by the cube root of 25 in order to make the denominator a nice number. So I'm going to multiply by the FFU cube root of 25 over the cube root of 25, because that's going to make the denominator the cube root of 125, which is regular 5. So my final answer here is going to be the cube root of 25 over 5. 19 and 20. If I look at this problem, I'm going to try and simplify it as much as possible before I get any further. So this is a square root problem. 12 over 27. If I reduce the if I reduce the fraction, notice that both of these are divisible by 3. So that's the same thing as 4/9. Well, that makes this problem much easier. So the square root of 4 is 2. The square root of 9 is 3. The square root of x squared is x. The square root of y is just the square root of y. And then the square root of z cubed, I can write that as z times the square root of z. But I need to do one more little thing in order to get anything done, because I'm not allowed to have a square root of z in the bottom. So I'm going to multiply by the FFU, square root of z over square root of z, because I need to have 2 z's in order to get rid of the radical in the denominator. So I end up with 2x root yz all over 3z. That's my final answer. Number 20, if I look at this, 16 over 32, since they're both inside of cube roots, I can simplify this before we even begin. So this is the cube root of 1 over the cube root of 2, which is 1 over the cube root of 2. I need 2 more 2's in order to make the denominator not have a radical. So I'm going to multiply the top and bottom by the cube root of 4. So my final answer is the cube root of 4 over 2.